All right. Before we start, I want to point out that if you look at the minor name at the bulletin board, there's a digital version of the textbook that you can use. If you prefer a paper copy, I can get you a paper copy after class today. Okay, not a big deal. Either is fine, whatever you like. If you decide later you want a paper one, and today's not the only day you can take one. So, cool? Yes?
So are we allowed to check one out for the whole year?
Yeah, of course.
Okay, because I like papers.
Yeah, no. That's exactly what I'm saying. Yeah, we'll do it at the end of class. No biggie. I just didn't mention it yesterday or last time, so I wanted to make sure I said it, because at some point somebody's probably wondering, where the heck is my textbook? What do I do with this? You know? All right. So we're just going to take a couple minutes here to go through this thing I gave you guys on the first day. If you notice, maybe you didn't, all these are great. Everybody got the same score. You can guess what that was. Yeah, there you go. So again, it was fine. Most everybody drew an acceptable picture. So your picture should have been something similar to this. It doesn't really matter because I just said A and B. You could have put them wherever you like. And then our function could look something, oops. Most of us drew something similar to this that looks like a simple rational function. Okay? But really, you know, your two arcs could be both on top, could be both on bottom. They could have been on the, you know, the one on the left could have been on the bottom, and the one on the top could have been on the right, or the one on the right could have been on the top. So all would have been fine, acceptable picture. If we label these like 1, 2, 3, 4, the end behaviors for these, number 1 should be the limit as x approaches negative infinity of f of x should equal b. Again, as I'm coming along, we would just say if I look at this end, that's like negative infinity comma b is that point. So the x is going to negative infinity and the y is going to b. For 2, we'd say the limit as x approaches a of f of x is going to equal positive infinity. And then likewise for 3, we would have written a limit as x approaches a of f of x equals negative infinity. But this is not quite right because we know that like a value for x can't have 2 different y's, and that's kind of what we're doing here. So we have to be a little bit more specific. So this end that's happening with the a's that are technical, or the x's that are technically less than a, you put a little superscript negative sign on there to indicate that we're looking at the values of x less than a. So we're looking at as x approaches the values of x less than a. And then this one we'll put a little plus sign. It'll be the values of x that are greater than a. So everybody kind of jog their memory on that. Remind you, yeah, maybe, no. We're going to talk a lot more about limits today and tomorrow and the next time. So even if it's not perfect today, that's okay. We'll get there. And then this last one, you know, that's like the point positive infinity comma b. So we have x approaches positive infinity of f of x is equal to b. Okay. So that your answers could have varied a little bit on, you know, these two, depending on how you drew your picture. You might have had slightly different answers, but 1 and 4 would have been the same regardless of the picture you drew. No.
I'm sorry, this might be a stupid question, but
No such thing. Go ahead.
Okay. So what would you label like y for these? So as x approaches a, like where would y like?
Okay, so if I look at that, yeah, that's kind of like a comma positive infinity, right? Because the arrow's pointing up.
Yeah, because a is approaching. Okay, got it.
That's kind of like that, right? if you want to think about it as like, okay, what's the point on that arrow? And that's kind of how we did it last year, right? When we were in trig and pre-calc.
Yeah.
Is we didn't do any technical definition of a limit. We didn't even define what it was. We just said we can do this to describe our end behaviors.
Okay.
And we did nothing more than that with it. Before I started on the notes, I want to point out to you, if you look in your OneNote now, we had talked about that the tests I did last year were too big. I covered too much stuff before I had a test. So I kind of tentatively put in, test every so often, where after I felt like that was enough to do a test. Some of the tests, you notice, are going to span like a little of chapter 2 and a little chapter 3 kind of thing. But I tried to shoot for about 5 sections and tried not to have too much of the meaty stuff in one test or the other. So I did that on there, and that's tentative. Obviously, as we get a little bit closer, we'll nail that down, but that was kind of my idea right away. I don't know if that helps or not, but I put it in there just for a heads up, since we're not going to be doing it just at the end of the chapters, right? Because they're too big. All right. So this first semester of AP Calculus, well, really, AP Calculus is divided into 3 kind of parts. So we're going to talk about limits. That's like chapter 2. We're going to talk about an operation called a derivative. So in chapter 3, we're going to do like all the algebraic part, like all the symbol manipulation part. Chapter 4 is going to be applications, like what kind of problems can we use a derivative to solve. Chapter 5 is going to be something called the integral. That's like the counterpart to the derivative, like the inverse operation to it. And then chapter 6, 7, whatever after that are kind of all applications using that. So in the second semester, we're going to get we'll do chapter 5 and chapter 6, and then we're going to do some sprinkles of other stuff. Since not all that stuff is AP required, I'm going to just kind of pick out the AP stuff, and time permitting, we'll do some of the other stuff that I think is particularly relevant if you're potentially going to be an engineering student going to take several years of calculus, right? Because I'm sure there's a couple of us in here, at least, that are planning on that as a potential career, or even a career where you're going to have several years of calculus also. So we'll get a little bit of exposure for those situations as well. Okay. Everybody feeling all right? All right, let's start talking limits. So in section 2, we're going to be talking about the limit of a function. So there's kind of 3 ways that we might evaluate a limit. We might do this graphically, just by looking at a picture of the graph. We might do this tabular, as in looking at a table of values, or like a set of points. And then the last way we might do this is algebraic. Now, today, really everything we're going to be doing is going to be graphical and tabular. As we move throughout the chapter, we're going to build out the algebraic piece. And the reason we want to do it in this order is really when we're doing this graphically or tabular, what we're doing is really kind of making a guess at what the limit is. Now, it's a pretty good guess for the most part, and we can do a good job with these things, and they're effective tools. But at the end of the day, it's still kind of a guess. When we develop out these algebraic methods, there's no more guessing. We're going to know. That's great. And 2, if we do a good job, we'll eventually just be able to look at the function and know what the limit is without really having to generate a graph and look at a picture and do some zooming, or build out a table of values, which is both of those things can be kind of time consuming, right? So that's kind of where we're going here for the next couple of days, as we're just talking about limits. Everybody's okay? So we've used limits before, but we've never really talked about what a limit is. So let's start with the definition. So what we're going to read here is the textbook definition for a limit. This is really precise and mathematical sounding and pretty opaque at first glance, and we're going to kind of talk about what this means with respect to looking at a picture or a table, so it becomes a little bit more clear. But our definition says, suppose f of x is defined when x is near the number a. What that means is it doesn't have to actually be defined at the value a, but just some neighborhood surrounding it. We write that the limit as x approaches a of f of x is equal to L if we can make the values of f of x arbitrarily close to L, but not necessarily equal to a. Oh, I'm sorry. Arbitrarily close to L by taking x to be sufficiently close to a, but not necessarily equal to a. Woof, right? You read that and you're like, whatever, I don't know what that meant. That's a normal response. Let's look at an example and kind of talk through what that definition is saying with respect to the picture. Okay? This is probably going to be the most helpful pieces. We want to understand, like, okay, I know what the definition says. That doesn't mean anything to me. How do I kind of use that definition to look at a picture, build a table, or whatever to get an answer out of this, right? So let's look at this example. It says the limit as x approaches 2 of the function x squared minus 2x plus 2 is equal to 4. So here I've drawn the graph of x squared minus x plus 2 in blue. I've placed the value x equals 2. I labeled 2 on the x-axis, and I drew a dashed line up to where the function is, where f of 2 is in our function. And I drew a horizontal line across from that value to the y-axis so we could read what the value of f of 2 was. In this case, f of 2 is equal to 4. Is everybody okay with that? Okay. So what the definition says is that we say the limit as x approaches 2 of f of x is equal to 4 if I can take values arbitrarily close to 2 and or I can get closer and closer to 4 by taking values closer and closer to 2, right? So let's say I start with this value right here. That looks like 6, and I can get that by making x equal to 3, right? If I want to get a little bit closer, say maybe to 5, looks like I can get that by taking like 2.5. The closer I'm getting to 4, the closer my function gets to the matching, or the corresponding x value is getting to 2. Does everybody kind of see what we're saying? We're getting arbitrarily close to 4 by selecting values that are getting closer and closer to 2. The other way to think about this is if we slide down our function as we're getting closer and closer to 2, the y values are getting closer and closer to the number 4, right? Until we actually get to 2 when our function is equal to 4. What I drew in yellow there would be like a right-hand limit, which is exactly what we did here in green. And this one then would be the left-hand limit. Oops, forgot the word hand. So just some vocabulary thrown at you. We'll circle back and do that again a little bit later, but it makes sense to just kind of say it now. Chanel.
Wait, so I don't understand. So is it as the x values approach 2, the y values are approaching 4? Is that how it works? Like as you're
So the definition says that if we want to get, we can make the values of f of x closer to L by taking the x value sufficiently close to A. So if we want to get, I can get 4.5. I start at 5, I go to 4.5. I can get there by getting closer to A. And I go to like 4.25, get a little bit closer to A. And then, it starts at the y and then goes to the x. But you could do it the other way. It doesn't matter.
Okay, so like for example, so the orange line is like 3, for example, so you're getting closer to 2 in that
Well,
result.
this is like 5, right? So we're getting closer to 4,
Okay,
and the corresponding x I need is also closer to 2,
okay,
right?
thank you.
Is there's a relationship, basically, right?
Okay.
Like if I squeeze down the y coordinate, it also squeezes down the x coordinate.
Okay.
Okay. Now we'll look in section 2.4 at another definition of a limit that's even more precise than this one. This would be the kind of definition that you could use to prove that a limit exists, or that to prove that your limit is correct. That would not be part of the AP curriculum, but if you're a potential engineering student, you will definitely do this kind of work in class, and we'll dip our toe into that section. We won't go heavy into it. It'll be like, we'll do like 20 or 30 minutes and then we'll move on. But we'll do some more we'll look at another definition that's even more precise than this one in a later section, just to give you a heads up. What would this look like if we investigated this limit tabular? So what I might do is build out a table of values where I start on the left side of 2 and get progressively closer to 2, but still stay left of 2. And look at how the y values are changing. I go from 2 to 275 to 344 to 371 to 385 to 397, 398, 399. Looks like we're heading to 4. And then I would want to check to make sure I can do the same thing to the right of 2. So I start at 3, progress down to like 2.001. And if I look at the y's, we go from 8, 575, 464, 431, 415, 403, 401, 400. Looks like we're heading to 4. Is everybody okay with kind of what we're seeing in the table and what we're seeing in our function or in our graph, right? Yeah? Now, in this previous example, we saw that the limit as x approaches 2 of f of x is equal to 4. And we noticed also that f of 2 is equal to 4, right? If I just evaluate that function at 2, the y-coordinate is 4. Everybody agree with that? Because right here is the point. Let's do a different color. Is the point 2, 4. Everybody cool? That does not need to be the case. Let's look at a couple of examples. So this is the example that we just saw, right? Where the limit of f of x as x approaches a is L, and f of a is equal to L. Right? So this is a case where we are continuous, f is continuous at a and defined at a. If I look at the next graph, if we follow along from the right, it looks like we're heading to L. And if I follow along from the left, it looks like we're heading to L. But when I look at f of a, it's not to L, it's actually whatever this value is. Right? Because you have the open circle, and you have like, what's this called when you have a discontinuity like that? Does anybody remember? Yeah, it's a removable discontinuity, or a jump, really, in this case, since the value is there. If it was just this one where it's just flat out missing, would be more like the removable. But still here, we would say the same thing. Oh my goodness, come on. Stay put. Okay. You stupid thing. Have moved on me too many times. Yeah, I just need a minute here. This all. Okay. Where's that? Probably right about there. Continuous at A and defined at A. And I'm just going to I'll just erase all that stuff. So here, again, the limit as x approaches a of f of x is L, but f of a is not L. So this is a situation where we are discontinuous at A, but we're still defined at A, right? I can still evaluate f of A. Nolan?
Is that say x approaches A, the second one?
Yes. Yeah, they're all going to say x approaches A. Yes, Chanel?
So for the first graph, how come for the limit f of x is equal to L, it would not be x is equal to A? Because it's like, isn't it at one point? Like, oh, it says right there f of A equal L.
Yeah,
Oh,
I just
okay.
didn't write it in.
Okay,
Yep, I
sorry.
said it, I forgot to write it.
Sorry.
Nope, that's okay. I just wrote it in a second ago, so you didn't miss it. You were just writing something else, and then you saw it was there. How did it get there? You're asking about something that I just written in. Yep, you're good. No worries at all. And if I look at the third one, again, if I followed my function from the left, we're heading to L. If I follow my function to the right, heading to L. But again, you notice we have that open circle at L. Well, the limit's still L, but f of L, or f of A here is undefined. So here we are discontinuous at A and undefined at A. Notice that all three of these situations, the limit is the same, right? So f of A could equal L, the limit, that's fine. F of A could equal something else other than the limit still exists. Or f of A could not equal anything, could be undefined totally, and still the limit could be the same, right? Everybody's kind of sees that. So I don't want to get into the habit of like, you know, that the limit is the same thing as what the function evaluates to. It's not necessarily. It could be, but not necessarily. We okay? Okay. All right. So let's do a couple of examples. Have you guys, well, we'll do the first one maybe together, right? So let's say we want to figure out the value of the limit as x approaches 1 of x minus 1 over x squared minus 1. So I'm going to use either a graphical or tabular method, and usually I try to do both and make sure that I'm kind of getting the same value each way. So I'm just going to start by firing up my calculator, opening up the y equals menu, and I'm going to type in my function into the y equals menu. In this sort of situation where there's a fraction, I like to use the alpha y equals to open the fraction menu and choose the fraction command where I get that horizontal bar. It just makes it easier to type this stuff in because I don't need like a million parentheses. So I'll just type it in just like it looks on my sheet of paper. And now I'm going to graph this. So I don't really know what I'm going to be looking for. So I'm going to start just by doing a zoom standard. Again, I haven't opened my calculator in potentially months, so who knows what my window was set at last. I'm just going to do a zoom standard to start. Now we're concerned with what value of x? 1, right? The stuff around 1. So if I look at my function, it looks like the point, we have 1 comma, I don't know, 1 maybe or so that I'd be interested in is this little region right in here. Does everybody agree with that? So I'm going to zoom into that just by changing my window. I'm not going to use the zoom on my calculator. So let's say I pick something a little less than 1 as my x min and a little more than 1 as my x max. And then probably 0 to 1 on the y should be sufficient. And let's just kind of take a peep at what's going on now. I'll hit graph. So this is my picture I get. What do you see right there on the function? Yeah, it's a little gap there. It's hard to see, especially if you're in the back. But I do see a removable discontinuity here at x equals 1. Notice there's the tick mark for x equals 1 right there. Is that a problem for us in evaluating a limit? No. So it looks like the left-hand side is going to that same value and the right-hand side is going to that same value. The question is just what that value is. Well, if I hit the trace button on my calculator, down here it tells me that I'm at the point x equals 1, and then there's nothing for the y. Why is there nothing for y there? Because that's where the discontinuity is. So there is no y coordinate there. If I take 1 tick to the left, I have 0.997, comma 0.5005. And if I did 1 tick to the other side, I have like 1.002, comma 0.4999. So it looks like from both sides we're heading to the value of 0.5. Right? The y coordinate, if I look at each side of it real close, is 0.5. It's continuous all the way there. That's my limit. Now, I should also check this with a table. What's the easiest way to do that? Well, I would do vars and then over to y vars, choose the function option and then the y1. And then I can do y1 of like 1.1 down to like 1.01. Notice that by pressing second and enter, I can just recopy the thing that I just typed in last and go back and edit it. So I don't have to jump through a bunch of menus to get that y1 again. But if I look at the values bigger than 1, as I check, I'm getting closer and closer to 0.5. I would do the same thing then for the values less than 1. So maybe I'd start at 0.9. And do the same thing. So 0.9, and we'll try 0.99, and then try 0.999. And I'm seeing the same thing. We're heading towards 0.5. So I'm real positive the limit is 0.5. Does everybody feel good as to what I did here to check? Chanel?
So does it matter whether or not you do it graphically or this method?
Tabular?
Yeah.
I would do both. I would check both because we're going to see in a minute where one or the other could give you maybe some misleading information.
Okay.
Okay? So I would try to do both. And you guys, will you remember what this y1 notation means when I'm doing this on my calculator? When I write it like that, where I do y1 parenthesis number. What the calculator is doing is just taking that number and plugging it into the equation that's in y1, just like a function notation would, right? So this is just a quick way to get a bunch of values tabular without having to like, pull the values from the graph or to make a table in the calculator, which is not usually helpful, especially if you're having like a decimal point is changing each time. Okay, everybody feel okay with that? All right, try doing number 2 on your own. I'm going to put a little 5-minute timer on this, and then we'll kind of go through things.
Is it bars and y bars and functions?
Yes, to get to the y1, exactly. Uh-huh. And when we're doing this kind of thing, you're perfectly fine to like chat with your neighbor and ask like, hey, what'd you get? Like, what are we doing here? Like, this is what I'm trying to do. Is this, like you can talk to each other. That's fine. I get this is the first one. You're trying to do it all on your own. That's great. Just letting you know that's okay since nobody has said anything yet. Just to be clear. You guys can talk and compare answers and all kinds of stuff. Chanel?
Could you also use the table function of the graph? You know how you click second table to like see the table values? Could that also be a method?
The problem is that it's going to be really slow getting closer and closer.
Oh, okay.
Right? Because 0.9 to go to 0.999 or 0.99, you have to like reset your table to something else.
Okay.
Either that or you set it at 0.01s. Now you have to press it 100 times.
Oh, okay, got
Or
it.
10 times to go, 10 times down to get to 0.99. And if you wanted a 0.999, now it's like so many times you have to press the down arrow to get it's just slow.
Okay.
You know what I mean?
Yeah, thank you.
You could use it, it's just a little unwieldy
All right.
and slow. I like doing it what I showed you because I can just pull the values exactly that I want.
All right.
But it's not wrong to do it that way.
Yeah.
Oh no! That's scary, isn't it? It startles me every time I get it too. Okay. What did you guys get?
0.167.
Okay. 1/6. Somebody else said. That's the same thing, right? 167 is approximately, or 1/6 is approximately 1.1 or 0.16, right? So either one is okay. Did anybody get something weird to happen when they were graphing?
It was like a straight line.
Mr. Floyd, you can show us an example how to do the graphing again, like when you were looking at the discontinuity.
Sure. So I just typed this in,
Okay.
right?
Okay.
We'll start with just the zoom standard.
Okay.
So I do my zoom standard. I just get this little whatever here. So we're interested in the area around 0. And looks like between 0 and 1 on the y should give me what I want. So maybe I'll do negative 0.1 to positive 0.1 and go from 0 to 1. Right? So here's that. That's what I get. Looks like just a straight line. Whoop-de-dee-doo. If I had turned off the axes, you can see the removable discontinuity right there. It was hiding on the axis, which not surprising because if I plug 0 in for t, I'm going to get 0 in the denominator, right? And if I zoom in a bunch of times, look at what you might have run into. So let's say I zoomed in a lot. Let's put the, oops. Ugh, Mr. Kulik, you dumb. Okay, that should be good. Oh, I should turn that back on. Look at what happened. What's it look like the limit is approaching this time? Looks like 0, right? It was looked fine before and I zoomed in too much and now this happened. What happened on my calculator? Why did it do this?
The same thing happened when I put in like y1 0.00001.
Mm-hmm. Yeah. So what happened here if we start zooming in too far or taking too fine of a grain on our table? There's a computer answer is actually the funny thing that's happening here. It's not an error what's happening. I mean, the calculator is making a mistake, but it's not like an error inside of the calculator. But your calculator can store, I think, 99 decimal places. All this is saying is that there's zeros all the way to the 99th decimal place, in which case it loses everything after it, and it calls that value 0. So we do have to be a little bit careful when we're looking at zooming into a graph that we don't zoom in so far that like the decimal point just disappears and we get to 0, right? Yeah, it's a small number, yes. But that is what's happening is your calculator is just getting all zeros before the decimal point has to truncate. And it's calling all that stuff 0. Does that make sense?
Yeah.
So again, this is the point of us doing these examples to show you like, oh, what could go wrong? So yes, good. Let's try the next one then. So again, we'll do 5 minutes again, and we'll try this next one. Good question. In AP Calculus, your calculator should always be in radians. Hi, Giselle.
Is there something wrong with it? It's like I don't know. That's why. I was like, why is my VARS not working? Thank you.
You're welcome. If you're still having problems, come see me again. But
Okay.
looking at your graph, I immediately knew the problem.
Yeah.
So things where it goes really small, does that count as part of the answer? Like, should it count as part of the
When I got it to go to 0, no, that's me showing you that like what could happen if you're being too specific, like you're zooming in too much, you're taking too fine of a grain. Right, you just have to do in the neighborhood of, and it's gonna be okay.
Okay, no, I still see that this is
Oh, I see it. That's all I was doing. Example 5.
Yeah. No.
What do you get?
Side X.
I did example
So
5.
you could do like,
Oh, I got it.
you could do like
What'd you get?
Now we should be doing 3, guys. Example 3.
See, I didn't notice you scrolled, so I thought it's 5.
I'm sorry.
Where is it? What's your
you got really soon, so you gotta really.
What do you guys think? We're ready to talk about this one? Did you get 1?
Yes.
That should be what you got. Nothing really can go wrong on this one, other than being in the wrong mode, which some of us started off in degrees, and we're like, this just looks like a straight line, which is weird. Again, I just typed it in and did zoom trig, and I'm pretty happy with just looking at this to say limit's going to 1, right? If I track along here and I track along there, nothing weird seems like it's going on. It just looks like we're heading to 1. That looks good enough to me. Chanel?
Wait, sorry, Mr. Bullock. How do you do the parse thing again?
So I press from the home screen, I press vars, I go over to yvars, pick the function option, and then there's the y's.
Okay.
Okay. All right. This one's my favorite. Try example 4 next.
I haven't.
Wait, but what's wrong with that?
What?
I got a plan on. Does yours look like that? Yours looks like that. Yours looks like that. What? No. Oh my god, wait. Why does my graph look like this? You know what, I need
Did you
that.
make sure you typed in the same thing?
Oh, I did not put sign. Okay, that was.
Okay.
Oh, nice. This looks so funny. This is a cool spiral. So is x approaches 0? Oh my gosh. Why is it 0? That's what it's saying for me too. It's saying 0, yeah. Wait, guys, wait, there's an error. Look. Which means that there's something going on with us.
Like just one.
What happened?
How many of us are just confused?
Yeah.
What's the right answer?
Well, how many of us did we start with graph or table?
I started graph and I got a really weird.
Okay, you get a graph. I get this. This is just me doing zoom trig to start. And I said, oh boy, I can't tell what's going on there just by looking at it. So let's zoom in a little closer, right? Maybe we'll just go negative 0.1, 0.1 to positive 0.1, right? Try it again. That didn't help. Maybe I should zoom in some more. Just kind of getting more staticky looking. All right, well, probably at this point, you're like, well, maybe we'll just try the table, right? So I try the table. Start at 0.1. I get 0, okay, great. And then 0.01. I get 0 again. Oh, that's not great. And I try 001 at 0. Okay, so now I'm confused, right? So it doesn't seem like I can figure out what's going on from the graph. If I do the table, I just keep getting zeros all over the place. Was anybody able to get anything other than 0 with the table?
I put in like Y1, 1.5, and I got 0.866.
Great.
So that's kind of far.
It is.
The X value is kind of far from here.
It is. Why do we keep getting, let's ask this question first before we figure out what's going on. Why do we keep getting 0 when we do this?
Because too many zeros.
Nope.
Oh, really?
It's not because it's getting too small. This is getting us 0 all the time for a different reason.
X is the denominator of the sine thing. So it's just sine of 0.
So when I do, let's say we're just doing sine of pi over 1 or 0.1. right? 0.1 is the same as what fraction? 1 over 10, right? So I could simplify this to just being 10 pi. What's 10 pi in the unit circle? Sign is 0 at 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So sign of 10 pi is 0. If I do 0.01, that's going to just be the sign of 100 pi. What's that going to be?
Same thing, 0.
0, right? So, okay, now I see. Okay, so what if I did like, 0.6 here, right? That's 3/5. That's going to give me a fraction of pi. That'll be good, right? So maybe I'll just do like, y1 of 0.6 and then get smaller each time. You think that's going to work? Great, not 0. Bah! That's not great. Try keep getting smaller. What am I getting?
Same number?
Yeah, it's just going to cycle through the same number of positives and negatives. Is that helping me get closer to something? Nah. All right. So what do? Doesn't seem like I can do this with a table, right? I tried to outsmart it, even have noticed what was going on, why I kept getting zeros. What? Nah. Okay. There is no limit. We say does not exist. Mean Girls fans, you should recognize this, right? What's the answer at the end of the movie? When she's at the math bowl? The limit does not exist. That was the answer at the end of the movie.
Oh yeah, I remember.
Right? Yeah. So really the graph should have been enough to us. Because if we think about what our definition is, I should be able to get closer and closer to a specific y value and get closer and closer to a specific x value, right? Or by getting closer to that specific x value. But the closer I'm getting into 0, it's just staying bumpy. I zoom in some more, just stays bumpy. I zoom in some more, just stays bumpy. Is it settling down to a specific value? No, right? Inside of every zoom, it's still bumpy as heck. It doesn't ever smooth out for me to tell what's going on. This should have been enough for me to just say the limit does not exist. The table was going to fool me there. Does that make sense to you guys? Okay. All right. We're going to skip example 5 because this one works and it's not a big deal. It's just kind of annoying. It's like it settles down to like 1 over 10,000 or 4 zeros and a 1. You would have been able to find it tabular or graphing. It wouldn't have been difficult. It just looks really close to 0. So the temptation is just to call it 0. It's not. It's like 1 over 10,000. But in the interest of time, I'm going to skip that. Okay. So we're going to talk next about one-sided limits. Remember we had kind of talked about this already a little bit when we mentioned when we do like as x approaches a from the right and x from the left or the right hand. Boy, I'm dumb. It's the wrong way. Look, the things that are less than a are on the left and things that are more than a are on the right. We've already kind of talked about these handed limits. So let's consider this function. This is called the Heaviside function. I'm just introducing it to you now. There's no reason you would have seen it before. It says h of t should equal 0 if t is less than 0. So any negative value of t outputs what value? 0. And the h of t should be 1 if t is greater than or equal 0. So any non-negative number outputs 1. Everybody cool with that? Well, if it's equal to 0, it's 1, right? Because it's or equal to. So no problems, right? So if I'm looking at the limit as t approaches 0 from the left, the values that are less than 0, what does h of t got to be? 0, right? Because if I graph this thing, it looks like this, right? So if I follow along from the left, we're heading towards 0. What's the limit if we go from the right? 1. Notice here that the left hand and right hand limits aren't the same. That can happen, right? But what does that mean for us? Well, we have this new definition that we'll introduce here. It says that the limit as x approaches a of f of x equals L if and only if the left hand limit and the right hand limit are also equal to L. In this case up here, because the left hand and right hand limits disagree, we would say the limit does not exist at t, or as t approaches 0. Everybody okay with that idea? That if the left hand limit and the right hand limit disagree, the limit does not exist. Now, this was a different reason than that previous example we looked at where the limit didn't exist, just because it never settled down. This is a different thing going on, right? A different behavior. This happens a lot in AP Calculus. Limits not existing because the left hand and right hand limits disagree. Them oscillating wildly and not settling down to anything is rare. That doesn't happen very much. Okay. All right, let's do an example here. So we are given just the graph of a function. Can I do a tabular thing on this? No, because I don't know what the equation for g of x, so I can't do anything with that, right? I have to just rely on the picture. That's all I got. So the first one is the limit as x approaches 2 from the left of g of x. So here's 2. So I'm just going to follow the function starting at the left until I get to 2. What y value are we approaching? 3. Everybody agree? So we just say that's equal to 3. Now we're doing the limit as x approaches 2 from the right of g of x. So I'm just going to start on the right of it and go back towards 2. What y value am I approaching? 1. So what does that tell me about the limit as x approaches 2 of g of x? Does not exist because the left-hand limit and the right-hand limit were different. Chanel?
Wait, I don't understand. So why is it does not exist? Is it?
So the left-hand limit went to 3. The right-hand limit went to 1. Because the right-hand and left-hand limits disagree, we don't have an answer for the limit.
They have to, like for example, they have to both equal 3 or equal 1.
Because again, when we define things mathematically, they need to be well defined. They can't give me 2 different answers for the same thing.
Okay.
Right? Should I pick 3 or should I pick 1? Because if I go one way, it's one answer. If I go the other way, it's a different answer. What do I do? Well, it doesn't exist. Okay. Let's see. We have x approaches 5 from the left. So 5 is here. So we go from the left. It looks like that's going towards, I think that's 2 though, right?
Is that an open circle? Is that right?
It does not, right? We already looked at that, right? When we went back here, right? These all had the same limit, even though one's continuous and defined, one's not continuous but defined. and the other is not continuous or defined, but they all had the same limit, right? Okay. And then if I look at the right-hand limit there, it's going to 2. So the limit as x approaches 5 is 2, even though g of 5 is, I don't know, like 1.5 or something. Right? The function can evaluate to something different than the limit. That's okay. Chanel?
So wait, so what's the difference between there being like a limit and there being defined? Does defined mean like at this point it's equal to this, and the limit just means as it's approaching?
Right.
Okay.
So you're looking, the limit's like, okay, what's the pattern going on if I look close to that value? What should it be getting to? And then the function output is what it actually gives you.
Okay.
Right? Because it looks like if I just follow along the graph, oh, it looks like I should have the 0.52 there.
But there's a discontinuity.
But there's a discontinuity there. It's actually defined down there at like 5, 1.5 or something.
Okay.
Right. Everybody happy? So far, so good? If we go back to the first problem here, or this problem that we did yesterday, what can I say about the limit as x approaches a? Great. Why does it not exist? Because the limits disagree. One is positive infinity, the other is negative infinity. Right? If I go back and look at my picture, one end is pointing up, the other end is pointing down at a. Limits are different. The limit there does not, or the left-hand limit and right-hand limit are different, so the limit at a cannot exist. Let's look at the limit as x approaches 0 of 1 over x squared. Well, okay. 1 over x squared. And we'll just do a zoom standard on that. So it looks like the left-hand limit is approaching positive infinity, and the right-hand limit is approaching positive infinity. So the limit there is positive infinity. That's fine, right? So we just, our definition for this just says if a function is defined on both sides of a, except possibly at a itself, like it was in that previous example where I had a vertical asymptote at x equals a, not defined there. That's fine though. The limit as x approaches a of f of x equals infinity means that the values of f of x can be made arbitrarily large by taking x's sufficiently close to a but not equal to a. Right? So as I get closer to a from the left, the y-coordinate keeps getting taller and taller and taller. The same thing as I go from the right, the y-coordinate keeps getting taller and taller and taller. Both of them are getting taller and taller and taller, both going to positive infinity. So we have an infinite limit. No problem. Same thing works for negative infinities, right? If they're both going down, negative infinity. Okay? So notice, each one of these 4 situations that I've drawn here would constitute a vertical asymptote, right? So we're going to use limits now to define what it means to have a vertical asymptote. So if the left-hand limit is infinite, positive or negative, doesn't matter, we have a vertical asymptote. Like here and here. If the right-hand limit is infinite, positive or negative, we have a vertical asymptote. That's what we have here. Right? And if the limit is just infinite, not the left hand or right hand, but just the overall limit is infinite, positive or negative, that means we have a vertical asymptote also, which is what we just saw in this picture. Right? So any infinite limit indicates a vertical asymptote, whether it's a left-hand limit or right-hand limit or just a regular limit. All of those are going to indicate a vertical asymptote.
There's a vertical asymptote?
As long as it's x approaching a finite value.
Oh.
So if x approaches infinity, that's something different. We haven't talked about that. So limits at infinity is next section. We'll talk about those also. But as long as you're approaching a finite value, like 1, 2, 4, 0, 100, 1,000, 10,000, 150 billion, all finite values, and the limit goes to infinity, that's there's an asymptote there, or negative infinity. Right-hand limit, left-hand limit, total limit, doesn't matter. Okay. So if we look at this, what you're going to see is this limit is positive infinity, and this limit is negative infinity. So we'd conclude that the limit does not exist, but we do have a VA at x equals 3.
This is two separate questions.
Well, it just says find this one and find this one. And then I say, what do these limits tell us? So the one limit is positive infinity, the other limit's negative infinity, and then that tells us the limit does not exist, but the vertical asymptote is at x equals 3. Maybe I'll do that. Maybe more specific, right? I'll write that in and say that the limit at 3 for 2x over x minus 3 does not exist. And if you look at the graph, what are you going to see? You have like a horizontal asymptote at 1, a vertical asymptote at 3, and then you have like this end doing this, and this end doing that, right? Oops, other way around. This one doing this, and this one doing that. Sorry. Everybody okay? Chanel?
Yeah. So, wait. Oh, never mind. All right, I figured it out.
Okay. And I just did that in my head. There's no reason that you could do that in your head right now. This is just like Mr. Kulik thinking about it, right? So if the way I thought about this is I have a number bigger than 3. If I do 3 minus that number, I get a positive. If I pick a number bigger than 3 and put it in the top, I have positive. That's how I got the positive infinity, because I know anything that's coming out of this is on that side should be positive. If I pick a number less than 3, x minus a number less than 3 minus 3 is negative, but a number less than 3 is probably also positive. Positive or negative is negative. So that's how I know it's going to be negative infinity there. Just showing you how I eyeballed that so quickly, if you were curious. That was the last thing for today. What do the bolds mean in the problem set? That's the homework quiz numbers. How does that homework quiz thing work again? You'll have a partner. You get to use your homework. You'll get assigned a number. Answer the one that you're assigned. That's it, right? What do you want to make sure you do by next class? The bold ones, at least, right? Next class is Tuesday. Yeah, for sure.
So, like every class is a homework quiz?
Well, every time we have an assignment. Some classes we might take more than one day to do a section or something.
Oh, got it. Okay.
Right? But anytime we complete a section, we'll have a homework quiz. Unless maybe it's the day before, like the lesson before the test or something. You know, like, I don't know if I do one then, but, you know, almost every time. We're just going to do a lot more of these, but they'll be quicker and should be easier. Oh, hey, one more thing, peeps. Today, we didn't take a break at any point. Next time, will somebody remind me around halfway to just like Can we have like a little break so we're not doing like an 80 minutes straight of calculus? Because I'll just get going and forget.
You don't want to break.
I'm just letting you know, like, please, like, somebody try to remember and tell me to take a break. Because I'm just going to forget. I just get excited about the math and want to go, 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 go.